Swayam Prabha. Digital India. Educated India.
So, welcome to Introduction to Electronics class. We have been discussing applications of BJT. Today we are going to discuss biasing of bipolar junction transistor. Before going into that, let me recapitulate. I think at the end of the last class we were discussing two applications of BJT. One was BJT as a switch, and then of course we will discuss in more detail about the BJT's application as an amplifier. But let me just recapitulate whatever we have discussed as BJT as a switch. Okay, so in this case, you remember we have a circuit something like this, where this is RB, this is RC, VCC, and this is V1. Okay, so this is a typical circuit to BJT. When BJT acts as a switch, of course depends on RB and RC values and VI and VCC. So let's go through this. We can draw the transfer characteristic of this circuit to understand its performance. Okay. Now we can write equations both in the base this loop here, and also this loop in the collector emitter region. So if I consider, we can write like IB equal to VI minus 0.7 volt divided by RB, assuming that VBE on is 0.7 volt as usual. Okay, and that will give us IC, that is beta IB equal to beta right. Then of course we can find out V out, because V out will be equal to VCC minus the voltage drop across RC. Okay, so VCC minus ICRC, that will give us V out. Okay, now you see that we can have several situation of V out here, depending on the value of VI. Okay, if VI is less than 0.7 volt, then transistor is BJT is off. Okay, because this base emitter junction will not be forward bias, right? So in that case there is very little amount of current flowing through the BJT, and we can say that there is no voltage drop across RC. So this entire voltage will be across V out, will be across this transistor. Okay, so V out in that case we can write equal to VCC, right? So so if we what we just said, we said like so this is our BJT and this BJT is off. So if you measure voltage here, you will get this entire voltage V out equal to VCC when Vi less than 0.7 volt. Vi we are applying here. Okay. Now, what is the other situation? Other situation is you can apply Vi pretty large, so that the current flowing through IC is quite large value. So if Vi is high, okay, although this high is a relative term, then what will happen is BJT is on. Not only it is on, the IC is large enough so that this V out, so that almost entire voltage will be across RC. So this is nearly equal to 0.2 volt. Okay, we usually, the rule of thumb is we assume VC is equal to 0.2 volt at VC sat. Okay, VC saturation, we usually assume VC is equal to 0.2 volt. Okay, that is basically in deep saturation actually. Okay, so you see in this particular case BJT is on, that means you have almost, this is short, but I know in ideal switch it is, there should not be any voltage drop across that switch, but here it is, we assume that is 0.2 volt. Okay, right. So in this, so we can draw a transfer characteristic and say that between between 0.2 volt Vi between 0.2 volt and VCC. Okay, we can say that V out no, sorry, this is, sorry. So V out between 0.2 volt and VCC, we can say that the BJT is acting in the forward active mode. Okay, let's draw that transfer characteristics, and so I have Vi transfer characteristics means output versus input we are plotting. Okay, and you see when Vi is, say this is 0.7 volt. Okay, so say up to 0.7 volt, V out will be equal to VCC. Okay, and V out equal to 0.2 volt, that is in the that is somewhere here, okay. So this is your 0.2 volt, and between these two, okay, if you try to plot the relation between Vi and V out from this expression, okay, you will see that in the within that region it is basically V out varying with V in linearly. Okay, and so we can so this is your transfer characteristic. This is basically your cutoff region. This is basically your saturation region. Okay, where V out is equal to 0.2 volt, and this is equal to, this is your active region. Okay, so you see to operate BJT as a switch, we need to take BJT from cutoff to saturation, okay, to realize that a switch, because in cutoff region BJT is off, okay, and the saturation region BJT is heavily on, so that there is very little voltage drop across the switch or across that BJT VCE, which is rule of thumb is around 0.2 volt. Okay, this is in deep saturation actually. Now to be for BJT to act as an amplifier, that is the second application, okay, that we will discuss in more detail later on. What we have to do, we have to keep BJT in the forward active mode. So you remember we have a lot of ICVC during our, that is the output characteristics, okay, and we got this plot in one of the class we have discussed. These are for different values of IB. This is common emitter mode we are plotting, okay, and we also discuss that this is our active region or forward active region. This is our saturation region. Just now we and this is basically our cutoff, right? Now this active region, we have to keep BJT in the active region so that when we want to use it as an amplifier, so the corresponding load line we can plot, okay, you remember, and say this is my this particular IB is my Q point, okay, so that gives me the Q point at the output side. So this is VCEQ and ICQ, right? So we have to make sure when we are applying BJT as an amplifier that the Q point is such that it is in the active region, okay, so so that even if there is fluctuation, there will be fluctuation in the current and voltages, simply because when we use BJT as an amplifier, we will see that we will apply an AC input signal, okay. Say in this case, if we use CE configuration, okay, common emitter configuration, then that input signal we will use at the base, and so we will vary this see this base current, you see, we will vary this base current and say between IB3 to IB4 and IB2, okay, and that varies the corresponding corresponding ICQ, okay, and also this corresponding VCEQ. Anyway, that we will discuss in more detail later on. But what I am aiming at, that to use BJT as an amplifier where we want to amplify the signal, what we small signal which we have used at the input, say in this case at base, and would like to see the performance of BJT as an amplifier, we have to keep BJT in this active region or forward active region, okay. So we have to choose all the resistors we have to bias the circuit such a way that remains in the so sort of in the middle of this load line, okay, middle of this load line or in the active region, okay, so that even if there is, so that when there will be fluctuation of ICQ and VCQ, it is still remains in forward active region and it doesn't go to saturation or cutoff region. If it goes to saturation or cutoff region, then this signal there will be clip in the signal will cut, you see, because BJT will no longer act as an amplifier, acts as a linear circuit when it is in the saturation or cutoff, but when it is in the active region, we can assume that BJT will act as a linear circuit. As you see, our plot here, transfer characteristic plot here, V out is varying with V in almost linearly. Okay, it's not exactly linear, but almost linearly, and of course that depends on how we are biasing it, whether it is in the active region or not, and how, whether the signal is input signal is small or not. But the point I am aiming at is we have to bias BJT in such a way that BJT remains in the forward active region. Uh, so uh, so that put us the discussion of biasing of BJT. Okay, so we have to keep our IBQ, ICQ, that is the currents at Q point, voltages at Q point, etc. Okay, uh, sort of independent of different parameters. Okay, what are those we will discuss in a minute. So biasing, proper biasing will help us to keep BJT in the in forward active region. Okay, uh, so that it can act as amplifier properly. And second is BJT also different properties, like its dependence on beta will be reduced. Okay, or if there is any variation uh, in components, like say resistors. Okay, these effects can be reduced. Okay, so that we will see, okay, how this can be done. But biasing is very important, so that we can keep BJT in the forward active mode, active region, and also these effects of beta can be reduced, and effects of variation in resistors, which we will use to bias the BJT circuit, can be reduced. Okay, so that's the purpose of biasing. Let's discuss some of the biasing technique in this class now. Uh, one of the technique we would like to use or discuss is known as single resistor biasing. Now, if you don't bias the circuit, what will happen is you will not get signal properly. But what I mean is, as I said, that you have to keep BJT in the forward active mode. Say, for example, I am going through an example described in Rajab's book. Very nice example. They have shown the usefulness of biasing. So say we are applying an input signal here at the base, and this is a microphone. Okay, and so we would like to increase or amplify this microphone signal, which has a very small value, say 20 millivolt. Okay, now if you apply this 20 millivolt directly to the BJT, what will happen? We know this formula, delta IC is equal to exponential delta VB over VT, right? IS exponential delta VB over VT. So you see, IS is usually very small. Okay, uh, and say I don't know, picoamp or femtoamp order, and that will give us very little value of delta RCIC. Okay, so this so that the output what we get over here is very less. So it will not be able to amplify, BJT will not be able to amplify the signal, simply because BJT is not on. You see, VB is not good enough, because here we haven't applied any biasing, and we have directly applied a signal at the input of the base. Okay, so BJT is not on, and BJT is in fact is in cutoff, right? Because we have directly applied a 20 volt 20 millivolt input signal. Okay, so we can't do that. What we have to do, we have to bias the BJT circuit properly. So one of the biasing technique, as I mentioned, we will use is we will start our discussion is a single resistor biasing. Okay, in single resistor biasing, the circuit is like this. Here we have um, uh, through this collector resistance, BJT is connected to VCC, and there is another resistor which is RB. Okay, and this is emitter is grounded. So this is single resistor biasing, or also you will see some books it is written as simple biasing. Okay, in this particular case, um, what we want is the voltage here. Okay, and voltage here. So Vy should be Vy should be greater than Vx. Vx is basically VBE, to make sure that BJT is in the forward active region, you see. Okay, so we can simply write write the equations, say in this in we can write the equation along this line here. So we can write in the IB RB, okay, plus VBE, right, is equal to VCC, right. So this is your base current. Base current is flowing through RB, and this is giving you this equal to VCC. So IB you can write this. Okay, so with what about IC? IC is beta IB, we know. Okay, and that is beta VCC minus VBE by RB. Okay, and corresponding corresponding VCE we can find out. Okay, in the same fashion, because VC is VCC minus ICRC. Okay, because VC is here, this is your VCE, right. So this VC or VY is VY is we can find out by VCC minus ICRC, because IC is current flowing through this. So voltage drop here minus VCC minus voltage drop across RC will give me VY, okay, or VCE. So this is your VCE. So that is VCC minus RC beta VCC minus VBE by RB, right. I'm just putting the expression of IC. So this is the expression of IC, you see from previous page here. So you see, so this is so what is the condition that this transistor will remain in forward active mode is if this condition is valid. Okay, right. So this is your VCE should be greater than VBE for keep the transistor in the forward active region, right. Now so this is a very simple biasing technique. However, couple of things I would like to mention here. You see that this if there is any change in VBE, okay, there is any change in, because this depends on this condition depends on VCC minus VBE, right. So if there is any uncertainty or change in VBE, okay, that will change your VCE, Okay, right? One constraint with this circuit. Okay. Second in IC is basically depends heavily on beta in this case. You see, IC depends heavily on beta in this particular case, because the equation we have written here, you see, IC depends heavily on beta. Okay. So if we have to change the BJT for some reason, say BJT is not working and we are changing BJT, and then beta will change, and that will change the biasing point. You see, in this particular case of biasing, also we have to choose an RB here quite large. Okay. Because RB we have to choose quite large, because usually IB is of the order of microamp. Okay, so we have to choose RB quite large, because you see, IB depends on RB, and RB we have to choose quite large, maybe couple of hundred kilo ohm, or of the order of meg ohm. Okay, depending on your value of VCC. So these are quite large. Okay. So if it is in a IC integrated circuit, the RB will occupy a quite a lot of area in silicon. So this biasing is not good in a sense, for a couple of points I have just mentioned. One is this depends on VCC minus VB. So any uncertainty in VB will change your VCC. Okay. No, we any uncertainty in VB will change your VCE. Okay, because will change your VC. That is one point. And here IC depends on beta, so if you change your transistor, then your biasing will change. And also RB will be usually quite large, because we tend to have like beta, we tend to have IB quite a small value. Okay. So the second biasing technique we would like to discuss is resistor divider biasing. Okay. In this case, we replace that RB with two resistors which are in the as if voltage divider mode. Okay. So this is your R1, R2. So this is the point X, this is the point Y. Okay. So you see, we have replaced RB with R1 and R2. Now in this particular circuit, we can, if we assume that the current through this along this is much greater than IB, then we can clearly write this. Okay. Right, if we assume that this current through this is much greater than IB, and so if the base current is negligible, we can write this, and IC will be equal to IS exponential VB over VT. You see, so that is VB is basically your Vx. Okay. IC is exponential VB over VT, that we already know. So IS exponential we can write over R1 plus R2 VCC over VT, right? Because that is your Vx or VBE. Okay. So you see, this is your IC, and so this IC, one of the good thing is IC now is independent of beta. Okay. In this case, you see IC is independent of beta, but that is not the case in the previous example, right? Because in the previous example you see IC depends on beta. Okay, now so why this beta dependent is not good? Because as I said, if we need to change transistor, if it is a discrete circuit, if I need to change transistor, I might not have a transistor of same beta. In that case, your biasing point or your Q point is change. Okay, so to avoid that, if we have a circuit which is independent of or very little dependent on beta, then we will be in a better position as far as the stabilizing the Q point is concerned. Okay, now but if this assumption is not valid, if as we are saying, say this current is I2 and this is IB, so the as this thing we are writing, assuming that I2 greater than much greater than IB. Okay, but if this assumption is not valid, we need to redraw, we need to recalculate this in the form of V Thevenin and R Thevenin. Okay, you remember, probably you can remember V Thevenin, how to calculate Thevenin voltage and Thevenin resistance, I mean Thevenin equivalent circuit of this. In case of V Thevenin is equal to, we can write the V Thevenin by opening this amplifier circuit at point X. Okay, and see the open circuit voltage at point X. Okay, so if I do that, then we will have VCC. Okay, R1, R2. So this is your V Thevenin, because we have removed the amplifier and we are measuring the voltage across R2. Okay, so that is V Thevenin What about R Thevenin? In case of R Thevenin, we need to short. We need to again remove this. Okay, open this amplifier, and VCC needs to be shorted. If you short VCC, you see then R1 and R2 is in parallel. Okay, so we will have R1 and R2 in parallel because we have shorted VCC. Okay, so what I am doing, I am trying to find out I am trying to analyze this circuit. If we use this condition, then analyzing is very easy. But if we use if that condition is not valid, that I2 is not much greater than IB, in that case we have to take into account R Thevenin and V Thevenin. Okay, right, and in that case we can write Vx equal to obviously V Thevenin minus IB R Thevenin, because you see the new circuit can be drawn like this. R Thevenin and V Thevenin here. Okay, right. So if I draw that, if I remove that and everything and draw V Thevenin and R Thevenin, and rest of the thing will remain the same, then you can write. So this is your Vx. You see, Vx is VB basically, Vx equal to V Thevenin minus IB R Thevenin. Okay, and corresponding IC we can calculate Is exponential VBE over VT, that is Is exponential V Thevenin minus IB R Thevenin by Vt. Okay, so we and we can find out corresponding IB and so on. Okay, now the thing is here, if this condition is not valid, then you see it IC will depends on beta. Okay, IC will depends on beta, and if there is a change in if there is variation in R1 and R2, particularly if there is variation in R2, okay, here if there is variation in R2, then there will be, it is possible to show there will be lot of variation in the in this biasing, okay, or in the Q point. If there is variation in R2, there is lot of variation in the Q point, because Vx will change considerably. Okay, now how to improve this situation? Okay, the third example we would like to discuss now is biasing with emitter degeneration. In this case, instead of connecting emitter directly, what we will do, we are connecting the emitter to the ground through a resistor RE. Okay, again, if you do that, the beauty of the circuit is if there is any change in Vx, okay, why there will be change in Vx, maybe be variation of R2, okay, because of that there is change in Vx. Again, you can analyze this circuit whatever we have discussed already by assuming that the current here is much greater than IB, or you can use V Thevenin and R Thevenin and find out the expression. Okay, but intuitively we can say that if there is any change in Vx, okay, because of change in R2, right, that change in Vx will be absorbed across RE, because change in Vx, so delta Vx, okay, will because Vx is equal to, we can write VBE plus VRE. You see, Vx is VBE here, VBE plus VRE, voltage drop across RE. Now, if there is any change in Vx, that will be absorbed in two parts, because in the previous case, you see, in the previous circuit, any change in Vx will be absorbed by VBE only. So any change in Vx, there will be exactly same change in VBE, because Vx is basically VBE in this particular circuit. But if we use a resistor here, that will do quite a lot of good in the, as far as the Q point stability is concerned, because now Vx is now Vx is a change in Vx will be absorbed in not only in VBE but also VRE. Okay, so So that way we'll be able to stabilize this circuit. Okay. So now one of the so this RE is acting as a negative feedback here. So for example, for some reason, if the it can prevent a condition known as thermal runaway. What is thermal runaway? Thermal runaway is if for some reason temperature of BJT increases. Okay. Now if the temperature of BJT increases, that will increase your IC. Okay. And your IB and IC will increase. That will increase again the temperature. That in turn again increases your IB and IC. So it is a as if it is a positive feedback loop which increases current because of temperature, and then that current will increase the temperature again, and that increase in temperature will increase the current again. So this can cause even breakdown of the BJT because of the too much increase in current and temperature. Okay. So this problem can be solved by simply using this RE, that is acting as a negative feedback, because if we increase our if for some reason IC increases, okay, for some reason that might be change in because of so IC can increase for various reasons, maybe because of increase in temperature, okay, or maybe because of you have changed your transistor. Okay, you have changed your transistor, and maybe a transistor you are using which has a higher beta, so your IC say increases. If your IC increases, then your IE also going to increase. Okay, so the voltage here that is VRE will increase. Okay, so if IC increases, that will increase your IE. Okay, and that in turn will increase your VRE, that is the voltage across your emitter resistor. And if this voltage increases, then what will happen? That this will reduce VB, because your Vx is fixed. You see, say your Vx is fixed. Now what we are discussing for some reason your IC increases, but your Vx is fixed. So if your VRE increases, okay, that will reduce your VBE. Okay, because Vx is VBE plus VRE. Okay, if this increases and if this remains fixed, that means your VBE will decrease, and if your VBE will decrease, that will decrease your IB. Okay, and if your IB decreases, your IB is equal to so if your IB decreases, then IC will decrease. IC will decrease because IC is equal to beta IB. So you see, as if IC will decrease, then this problem will be solved. Whatever IC increases, IC, because of you are using this negative feedback, which will basically reduce VBE and reduce IB, and that will reduce your IC. Okay, so your ICQ and corresponding VCEQ will remain intact, because that's the purpose of your biasing. Okay, so we will see that in our discussion we will use RE. We will lot of discussion as an amplifier. We will use this circuit. or voltage divider biasing circuit. But RE has a very important role to play because it will absorb any variation in Vx, okay, and also any variation in IC because of change in beta or because of change in temperature. There is another biasing technique which I just briefly would like to mention before we self biased stage. Okay, in self biased stage, the circuit is like this. Here we have RC, VCC, and this is your RB. So this is your self resistor biasing. Okay, in this case you see Vy is equal to VCC minus ICRC. Okay, and so we can write Vy is equal to also IBRB plus VBE. Okay, and from here you can find out IC. The point to be noted in this case is Vx. Vx is Vy, so this is your Vx. Vx is Vy minus IBRB. Okay, so you see the transistor will always be in the forward active mode. Okay, now because Vx is less than Vy. Okay, so with this we are basically finishing our discussion. We have discussed several biasing technique, single resistor biasing, and voltage divider biasing, and emitter degeneration biasing. In the next class we will discuss BJT as an amplifier. Probably we will start with a small signal model, and then we will go from there and discuss the amplifier application of BJT in more in detail. Okay, so thank you very much for your attention.